Today's lesson is section 7.3 for Algebra 2, and we are discussing logarithmic functions. Today is an introduction, and we will be doing further work with them. We're talking about inverse operations that undo raising a power to an exponent, and that is called finding the logarithm. A logarithm is the exponent to which a specified base is raised to obtain a given value. One of the key ideas I want you to think about why we use logarithms, logs are, that's the short name for it, logs are used to find unknown exponents. So we just did some work with exponential growth and decay, and if you were given a problem where you were asked to find when it will be half the value or double the value, you were looking for an unknown exponent, and that idea brings up that we could solve it by using logs, not trial and error, not tables. So the big use for logs are to find unknown exponents. We're going to start by doing some basic ideas, and we're going to talk about the inverse. Exponential equations and logarithmic equations are inverses. So this is really important to know. So we have our exponential equation with a base to the power of x equals a. To change it to logarithmic form, the base of your exponent becomes the base of your log. This is read log base b of a equals x. So the base of your exponent is now the base of your log. It's written as a subscript down low. Logs are known to solve for unknown exponents. So x is my unknown exponent. The log is equal to the exponent. And then we are taking the log of our answer in the exponential equation. So log base b of a equals x. One of the ways people remember this is sort of a flow chart. And so your base becomes your base, and your x comes from up here on your power. So we just sort of bring the base into the base and the power into there, and then the a drops. Again, if you think about this, the base is your base of your power. Log solve for unknown exponents, so it is equal, the log is equal to x. So we're going to go ahead and practice converting these forms. If you look at this chart, everything in here is true. If I type in 2 to the 6, I will get 64. And so I'm taking this exponential form and I'm changing to logarithmic form. I'm not doing any math, just changing the forms. So this is 2 to the 6 equals 64. I'm going to write this as log base 2 of 64 equals 6. So the base is the base of my log. It's log base 2 of the 64 is equal to 6. And so if you want to look at this, it's log base 2 of 64 equals 6. There's a better idea of that flow chart. Log base 2 of 64 is 6. All right, 4 to the first is 4. That's true. So if we write this, it'd be log base 4 of 4 equals 1. I'm going to put a star beside this because this is one of our properties that we're going to learn. So log base 4 of 4 equals 1. Now, this makes sense to me. I know it's a true statement. Putting it in log form doesn't really help me unless I know my properties. So if I had log base 2 64, I'd actually want to put it back in the exponential because I can answer this. 5 to the 0 is 1. Anything to the power of 0 is 1. So we would change this. Log base 5 of 1 is 0. Log base 5 of 1 is 0. I'm going to put a star beside this because these are also properties that we are learning. All right, now I have a negative exponent. If you remember, a negative exponent flips it. So 5 to the negative second is the same as 1 over 5 to the positive second, and that's why we get that decimal point 0.04 because it's equivalent to 1 over 25. So this is, again, a true statement. Let's change it to logarithmic form. Log base 5 of 0.04 is equal to negative 2. Log base 5 of 0.04 is equal to negative 2. Your base is your base. Logs equal the unknown powers. All right, last one here. I could mess with this. 3 to what? 9. 3 to the third is 27, and 3 to the fourth is 81. So I'd have to take a little time to figure that out, but I know that x would be 4. However, we're going to change this. So this would be an unknown power, so I would come in and take log base 3 of 81 equals x. Now, the issue with having log base 3 of 81, that solves for x. The problem is your calculator, unless you have a different one, your calculator only does log base 10. So if we look at that log sign on our calculator right there, that log only is base 10. So I can't type in log base 3 or log base 5. So none of the problems here I can use my calculator for until I learn how to change base to base 10. And we'll talk about that being called the common log. All right, so we have a couple examples here. So using our rule up here, this is a good guide, something to put on a note card so you have it for reference. We are going to change these from exponential equations to logarithmic form. So I have 9 squared equals 81. My base is 9, my power is 2. So log base 9 of 81 is 2. That's sort of the flow there. Log base 9 of 81 equals 2. In the second one, we have log base 3 of 27 is 3. So log base 3 of 27 is equal to 3. So again, we're practicing putting this in log form. This log form with base 3 is not helping me. I would always take it out of log form and put it back to exponential to understand it better. All right, this next one says x to the 0 equals 1. Anything to the power of 0 is equal to 1. And the stipulation is that x can't be 0. 0 to the 0 is undefined. So that stipulation's there. This would change to be log base x of 1 equals 0. And if you come back up, this problem plays out like this. Log base anything of 1 is always equal to 0. So that's again one of our properties. Okay, now let's go the other way. We now have logarithmic equations. Let's change it to exponential form. And since our first one says log base 10, I'm just going to put this in the calculator real quick so you can see it. It's log base 10, and that's what my calculator is programmed to do. See how it says log, and right above it, if you can read it, it says 10 to the x. So I would just type in log 100. The base 10 is understood, and log 100 is 2. So my calculator will do that one. My calculator will not do any of the other ones because they're not log base 10. All right, so taking this, the base is 10, so the base of my exponent is 10. Log solve for exponent, so 10 to the second is equal to 100. And that's a true fact. So if I'm ever just trying to convert and I'm not sure of it, I can always try to look and say, okay, what makes sense in exponential form? What's going to be a true statement? So same thing here. Logarithmic form is very confusing. It's not helping me to understand what these numbers mean. Take it to exponential form. It's 7 to the power of 2 is 49. All right, next one. 8 to the power of negative 1 is 0.125. And again, that 8 to the negative 1, that is the same as 1 over 8. And that's why we get that decimal 0.125. Here we have log base 5 of 5 equals 1. So this is, again, I'm going to put a star there. This is one of our properties. When we have a log base 5 of itself, it cancels out. And here's why. It's 5 to the power of 1 is equal to itself. So 5 to the power of 1 is equal to 5. This is another one of our properties. Anytime it is equal to 0, it comes from this rule. Anything to the power of 0 is 1. So 12 to the power of 0 is 1. 12 to the power of 0 is 1. So it's very important that you convert. Most of the time I'm going to take something in log form and turn it to exponential, and that's also how we change base to solve them later. All right, so let's keep going with a little bit more practice. So we have some problems here. Log base 10 of 10 equals 1. I'm going to star, every time I star these, I'm bringing them up because they are properties that we're going to learn. So log base 10 of 10 is 1. Change this to exponential form. 10 to the first is equal to 10. Log base 10, so 10 to the power of 1 equals this. So the base is my base, log solve for exponents, so the answer is now my exponent. So this would be 12 to the second equals 144. Again, if it helps you to do this flow, 12 to the power of 2 is 144. So when we go to do this one, I have a base of 1/2 to the power of -3, and that equals 8. So if I write 1/2 to the power of -3, that's a little misleading because it looks like the power is only on the 1, so this should be in parentheses. So 1/2 to the power of -3 is equal to 8. I want to take this a step beyond because we're going to use some mental math to solve these. So why does this work? If I have 1/2 to the power of -3, that 1/2 to the power of -3 really becomes 2 over 1 to the power of +3, and that would really be 8. So I want to remind you that a negative exponent means we're going to flip our fraction, and that's going to help us when we do our mental math. All right, so here are the couple of the properties. So I'm going to put a star here because these were the ones I starred that we can reference back to. So we have that the log base b of b is equal to 1. So if you have a log base of itself, it always cancels out to 1. And then that rule comes from taking the base to the power of 1, give me back b. So here's your logarithmic form, here's your exponential form. An example, log base 10 of 10 is 1 because 10 to the first is 10. So if I forgot that rule, I could simply change it to from logarithmic to exponential form and figure it out. Here is the other rule, log base b of 1 is equal to 0. So anything to the power of 0 is 1. It doesn't matter what the base is. Here's your example. If I see log base 10 of 1, if I'm taking the log of 1, I'm going to get out a 0. 10 to the 0 is 1. So these are two rules, again, I'd be putting on a note card. I'd have a big note card with all my logarithmic properties on it. Okay, now I referenced this. A logarithm with base 10 is called a common logarithm. A lot of people don't think about it, but if we stretch this idea and we go to our square roots, we put a square root sign and we know that's a square root. If I want to show a cube root, don't I put a little 3 there, or a fourth root, I put a little 4 there. But truly, the square root symbol is written with the 2 there. But because we use it so commonly, we understand if we see this, it represents the square root. Any other root has to be represented by a number. That is the same thing. If there's no base written for a log, the base is assumed to be 10. So that's the common log. So if you see log of a, that is really saying log base 10 of a. It is understood because it's a common log. So if I'm looking at this one, and notice the directions say evaluate logarithms by using mental math. The ones that we're working on today are ones that we don't need to use a calculator on. So it just says log, and I know that must mean log base 10. So let's take this out of log form, even though I could use my calculator. Take this out of log form. It's 10 to some power equals 1,000. So I'm going to replace that question mark with an X. I like to fill in all the pieces. So 10 to some power equals 1,000. All right, well 10 squared is 100. 10 to the third is 1,000. So this must be equal to 3. Now, if we want to double check that, since it's log base 10, I can put that in my calculator. Log base 10 of 1,000, and that is equal to 3. And that is because 10 to the third is 1,000. All right, looking at this one, I don't have base 10, so definitely having it in log form does not help me. Again, I'm going to replace that question mark with an X or whatever variable you choose. I'm going to take it out of log form. So this log is equal to my exponent. That means 4 to some power equals 1/4. Okay, so here's what I'm seeing. I'm supposed to use mental math to do this. I see my 4, but notice it moved down. And what makes something move down is that negative exponent. So if I think about this being 4 to the negative 1, wouldn't that create the idea of 1 over 4? So my x value is negative 1. I kept the base of 4, but it moved to the bottom, and a negative exponent is going to move it to the bottom. All right, we have a couple more here, and it says evaluate using mental math. And one of the hard parts here is this decimal. We actually want to keep fractions if we're using mental math. If we're using our calculator, we can use anything. But mental math, I don't want this. So if we read this, first of all, it's base 10, and I'm going to set it equal to x. I always want all three parts. I think that's really helpful. So even though we know it's base 10, I like to fill that in. There's my base. It's equal to x. There's what I'm taking the log of. So let's rewrite this. This is really log base 10, and let's do the fraction. So 10th, 100th, 1000th, 10,000th, 100,000th. So this is really the same as 1 over 10 to some power. And so we had, again, 10th, 100th, 1000th, 10,000th, 100,000. So it's 1 over 100,000. And that's helpful here in a minute. And that's still equal to x. Okay, so if I change it to exponential form, that would be 10 to some power equals 1 over 100,000. And so I need to decide what power is going to get me there. The first thing I see is that this 100,000, it is a base of 10. Okay? I need a negative power to make it go down, and then I need to figure out what power is going to make it that 100,000. All right? So again, we know we need negative power to push it down. 10 to the 5th is 100,000. So if we type that in the calculator, 10 to the 5th is 100,000. So that means I want it to be a power of negative 5. It's going to give me the 100,000, and it's going to flip it to the denominator. Now, if I type in my calculator 10 to the negative 5th, I get back that original decimal. I just think it's easier to look at it as a fraction because then we see where the number is moving. Okay, in this problem we have log base 25 of 0.04. I'm going to set it equal to x. So we want to make sure we have all three pieces, and my base is 25 to the power of x equals 0.04. So I want to remind you again, if my number is getting smaller, if my number went from a base like 25 to 0.04, that must mean I have a fraction. So if you can think about 0.04, isn't that the same as 4/100ths? Now, if you're not comfortable doing that, just put 0.04 in your calculator, 0.04, and then we should have a fraction to decimal key. So for me, it's a second function, f to d, and it will change it to a reduced fraction. Some people need to change it and reduce it. So I got 4 over 100, which is the same as 1 over 25. And by looking at it as a fraction, I can now figure out what to do. In decimal form, I have no idea what my power is other than a negative number. Okay? The minute I make it a fraction, I still have my 25. It's just down in the bottom. So x is equal to negative 1. 25 to the negative 1 flips it to the bottom. So we want to use our fraction form. To continue our notes and show about inverses, to make a connection with our last lesson, logarithms are the inverses of exponents. The inverse of an exponential function, such as y equals 2x, is a logarithmic function, such as y equals log base 2 of x. Now let me talk about this a little bit. If we take our exponential function and we change it to logarithmic form, it'd be the log base 2 of y is equal to x. So log base 2 of y is equal to x. So this is our original exponential function, and this is the logarithmic form. And the first step to finding inverse is to switch x and y. So you can see in logarithmic form, its inverse is y equals log base 2 of x. So again, here is your original function exponential form. Here it is in logarithmic form. If we find the inverse of this function in logarithmic form, we have simply flipped the x and y. All right, this is a nice idea, that's something I would also add to my note card, just to help you remember. B to the power of x is a. That's just a quick reminder of how to change logarithmic form to exponential. All right, I want to talk a minute about graphs. So you notice the domain and range are switched by switching the x and y. So if we look at the domain of y equals 2x, the domain of y equals 2x, we find it's all real numbers. And so we have our graph here coming up, exponential growth. And so we write that this is y to the power, y equals 2 to the x. And so when we see this graph going, the reason the domain is all real numbers is as the graph goes up, it's going to keep pushing to the right. And so it keeps increasing for x. And as the graph goes, we see it push to the left and it increases. So again, the domain is all real numbers, and the range is y such that y is greater than 0. As my graph goes, it's going to continue up to infinity, but as it comes down, it's never going to hit 0. It's always going to stay just above. There's always a little bit left. And so that is why our range is y is greater than 0. The inverse that we talked about, the domain of the inverse, where y is equal to log base 2 of x, is the original range. So as my graph flips over the equation, y equals x, that is its line of reflection or symmetry, reflects over y equals x. We have our graph coming in, and this is the graph of y equals log base 2 of x. And so as this graph comes, the domain keeps going. X will be going to infinity, but as it comes in, it approaches 0, but it will never equal 0. And so that's why our domain is x such that x is greater than 0. And the range now is all real numbers, because as this comes in, we see it go down to negative infinity. And as it comes over, we also have to imagine that it's still increasing slowly, but it's moving up the y-axis. All right, let's move to an application problem, something that is used in chemistry a lot. So chemists regularly test rain samples to determine the rain's acidity or the concentration of hydrogen ions. So that is what we're looking at, is the concentration of hydrogen ions, H+. The acidity level is a pH level, and it's given by this function. It's not a function that needs to be memorized, but it is something that we should be able to apply and use. So the pH level is found by the negative, so -1 times log of H+, and the H+ is the concentration of hydrogen ions. Okay, H+ is measured in moles per liter. So we want to find the pH level of rainwater from each location. So let me remind you that we have the pH level equal to -log base 10 of H+. So we just have to find the moles per liter and plug that in. But I want to talk real quick about the range of the level. So from 0 to 14, those are the pH numbers, and 0 to 7, those are your acidics, those are acid, and then we sort of jump 7 to 14, those are our base, and I know I'm including 7 in both of these. 7 is considered neutral. That just gives you an idea. Now this graph's a little bit hard to read as the numbers are a little bit blurry here. So we want to find out the acidity in rainwater in central New Jersey. Okay, so this map's giving us the hydrogen ion concentration of rainwater in several locations. So if we want to find the concentration, we need to find our moles per liter, and we're just going to plug it in, and that will give us the value for the pH. So the pH in this problem is equal to -log of, and we want to make sure we copy this right. So it's a decimal and then 4 zeros and then 316. This is not math I'm going to do by hand. I'm going to plug it into my calculator. And so that would be negative, so negative sign, and then log. Make sure you double check your zeros, 316. I'm going to round it to nearest tenth. I think I have too many zeros. All right, there we are. I'm going to round its nearest tenth, and I get a pH level of about 4.5. So that is in the acidic range for rainwater. So that's central New Jersey. Let's compare that to central North Dakota. Again, I'm going to take my pH level, -log, and I have 1, 2, 3, 4, 5, 6 zeros. and a 9. Make sure I have that right. 2, 4. Okay. That's a 0 there. And we're just going to type that into our calculator. So 4, 5, 6, and a 9. Close my parentheses. And I get 6.04. So rounding to the nearest tenth, I'm going to say that the pH level is approximately 6. So this in central North Dakota pH level of 6 is closer to a base than in central New Jersey. Next, we can also check out the acidity of things like iced tea. And so I would use the same formula, and that would be negative log of, and here is my hydrogen ion concentration, 0.000158. Again, I am just going to type this into my calculator, negative log base 10, and I have 3 zeros, 158, and I get a concentration of about 3.8. And so you can see that that is definitely more acidic. If I would test lemon juice or orange juice, we would have an even higher concentration of hydrogen ion that would make it more acidic.